Okay, good morning. Today we'll look at 3 examples for chapter 4 and wrap it up. And then from Wednesday onwards, we get into the good stuff, AC analysis. So let me take an informal poll. The previous 2 sections overwhelmingly voted yes, and I'm assuming this section will do the same. The question is, do you want an extension for the homework that's due tomorrow? Show of hands. Yes, so consider it done. I will send an email or either post an announcement. I don't know how long I'm going to extend it. I will go through the problem, see how many students have completed it. And then either, because Wednesday we begin the new topic, so I try not to overlap 2 topics together. So either maybe a day or maybe 2 days, but it'll be extended. Okay, so let's go to the class notebook. There. Okay, so let's see. Example 1 is an inductor. Problem statement states that the switch in the circuit has been closed for a long time before it is opened at time t equals to 0. So if you look at the switch is right here. The first thing we should realize as soon as we read the words a long time, it means that it indicates steady state. Now it could mean either that the component is fully discharged or it is fully charged. In this case, if the switch was closed for a very long time, we can draw out the circuit for time t less than 0, meaning how did the circuit look before the switch was flipped open? We are not analyzing for the time before the switch was open, but we do need to know the we do need to know the circuit conditions in order to set up our analysis. Okay. So again, we are not analyzing for time t less than 0. We simply need to look at the circuit to determine the current or the voltage as soon as the switch is opened. So in this case, if the switch was closed, we have a current source, resistor, switch is closed, we have an inductor, and then 3 resistors on the far right. Now the key word is steady state. If it's steady state, it indicates inductor is fully charged. And if the inductor is fully charged, it behaves like a short circuit. And if it's a short circuit, then the circuit reduces to a current source and the short circuit wire, the inductor. All of the current from the source is going to flow through that inductor because the inductor is at maximum charge and the inductor behaves like a short circuit. Anything that is in parallel with a short circuit wire is effectively redundant because a short circuit wire has resistance of 0 ohms. If it's 0 ohms, it's the path of least resistance, meaning everything will go down that pathway. Nothing will go to the rest of the components. Okay, as long as they are in parallel with a short circuit, they are effectively redundant and removed from the circuit. Yes. 20 amps, yes. So thank you. 20 amps. So the inductor current is 20 amps. Now this is the circuit condition right before the switch is flipped open, right? Now at t equal to 0, switch flips open, what happens? The source and the 0.1 ohm resistor is disconnected. It's only connected at one end, meaning it's not part of the circuit anymore. It's disconnected. The only things left in the circuit are the inductor and the 3 resistors on the right. Right? Switch flips open at t equals 0. The only thing left in the circuit is the inductor and the 3 resistors on the right. Make sense? Right? So you draw the circuit for time t less than 0 and time t greater than 0. And then you look at the circuit to determine the initial conditions, the final conditions, and then the time it takes. Okay. So again, any of these problems, you simply use the standard expression. The standard expression has 3 quantities: initial value, the final value, and the time constant. So does the circuit have a source? Remember, the only circuit we are analyzing is the second one. This is the only circuit we are analyzing to generate our equation, right? We do not care about what happened previously, except to determine the initial conditions. So no source in the circuit. So is it natural response or is it step response? Natural response. The energy that is stored in the inductor is now being discharged through a resistor. So it's a natural response circuit. And if it's a natural response, what is the final value? It's releasing all of its energy, meaning at some point, the inductor current has to go to 0. So the final value, the end point of your analysis, IF, the value of the inductor current, will always be 0. If it's a capacitor, final value for a discharging capacitor will always be 0. So it doesn't really matter what the component is. If it's a natural response, the final value is always 0. So in this case, because it is natural response, IF is 0 amps. We have the end point value. What about the beginning point? II. When we begin our analysis, we have current through the inductor. Current through an inductor cannot change instantaneously, meaning the current in the inductor after the switch is flipped and before the switch is flipped is exactly the same. So the initial value of the current has to equal the current in the fully charged inductor, which is 20 amps. Okay, so current through inductor cannot change instantaneously. Therefore, II or I0 is 20 amps. 20 amps. So we have the end point, we have the start point. We need to find the time constant, the time it will take for it to go from the start to the end. So which resistor do we use? Tau for a inductor RL circuit is L over R. Which of the 4 resistors do we use? 1, 2, 3, 4? Or all of them? The equivalent resistance, the answer is absolutely correct. We are analyzing only this circuit. So the stored energy in the inductor is being delivered to all the resistors that are connected to the inductor. The resistors connected to the inductor are the 3 resistors on the right, as shown in the circuit diagram. All of them receive that inductor energy. So we have to find the total equivalent resistance, Req, as seen by the inductor. Okay, we have to find Req as seen by the inductor. And so that would be determined in the circuit. When you read the words as seen by, if you remember, you remove the inductor from your analysis and you find Req as seen by inductor L, which is, if you look at the far right of the circuit, $40 ohms in parallel to 10 plus 2 gives you 10 ohms. So tau, time constant tau, is L over Req. It's 2 Henry divided by 10, 0.2 seconds. Take a pause. Let me know if you have any questions. Any questions? Does the procedure make sense? Right? Yes. So the question being asked is, let me see if I understood it correctly, is if there was a resistor in series somewhere here, or perhaps before the switch. Am I correct? So in that case, no, it still wouldn't be. It would still be the same. So in that case, the current is flowing through the circuit. It'll still be 20 amps coming out. 20 amps would, some of it would go down here, some of it would go here, some of it would go to the inductor, but eventually the inductor will reach full charge. It would still be 20 amps. Now, if there was multiple resistors in parallel, still the answer would be the same, because at some point the inductor would reach full charge. Yeah, but we are not analyzing for the time t before 0. So in this case, it doesn't matter. But good question. All right, so let's see. Now that we have the 3 quantities, we simply plug the values into the standard expression. We can find IL of t, so IF plus I0 minus IF into e raised to minus t over tau. I'll plug in all the values. Final value is 0. I0, the initial, is 20 amps. And then tau is 0.2 seconds. Reduce the circuit after plugging in all the values. And you have 20 into e raised to minus 5t amps. And this equation is valid for all time values greater than or equal to 0. Okay, greater than or equal to 0. Let me know if you have any questions. At time t equal to 0, if you plug in the value for t as 0, you get e raised to minus 0, e raised to 0, which is 1 times 20 amps. Value for the current at exactly when the switch is flipped open is 20 amps. You plug in t as 10 milliseconds, 20 milliseconds, 30 milliseconds, you'll get a exponentially decaying waveform for the inductor current that eventually will go to 0. Mathematically, if you plug in a high or very large number for t, you will obtain a value for I. However, it's a mathematical expression. In real life, it will go to 0. Especially after 5 time constants, which is the standard accepted practice. After 5 time constants, it loses more than 99% of its charge. And so we say inductor is fully discharged. Any questions? Okay, let's see example 2. Similar to example 1, but this time we look at a capacitor. So it's a voltage equation. Switch has been in position X for a long time. Long time means it is steady state. X is on the left. Meaning the capacitor is connected to the voltage source. 100 volts. Resistor. And similar to the question asked previously, it doesn't matter that the resistor is in series. At the beginning of the problem, again, we are not concerned with what happened before the switch was flipped. So before the switch was flipped at time t equal to 0, capacitor is connected to the voltage source. Because it's been in steady state for a long time, eventually the capacitor voltage did reach 100 volts at some point in time. Capacitor at full charge behaves like an open circuit. If it's an open circuit, there is no current flowing through the circuit, meaning the resistor voltage is 0. If you apply KVL around the circuit, you obtain 100 volts at the source, 0 volts across the resistor, and 100 volts across the capacitor. Take a pause, think on that. Let me know if you have any questions. Any questions? Does it make sense? Right, it's a fully charged capacitor. Okay, at time t equal to 0, the switch is flipped to the right. We have a fully charged capacitor and a very similar resistive network to the previous problem. Capacitor voltage is now discharged to the 3 resistors. We find Req as seen by the capacitor. It's a natural response problem because there is no source. So the final value for that capacitor voltage has to be 0 volts. Capacitor voltage, like the inductor current, cannot change instantaneously. So the voltage in the second circuit, meaning after the switch is flipped, is exactly the same as the voltage in the first circuit, which was before the switch is flipped, which is 100 volts. So cannot change instantaneously. Therefore, VI or V0 is 100 volts. Tau is equal to R times C. In this case, it was REQ times C. REQ, similar to the previous problem, is a combination of 240K in parallel with 60 kilo ohm resistor plus 32K. And REQ is 8080. Therefore, time constant tau is REQ times C, 80,000 times 0.5 into 10 raised to minus 6. Therefore, tau is 4040 milliseconds. And final value, VC of t is VF plus V0 minus VF into e raised to minus t over tau. Oh, 0.04. Hundred into e raised to minus 25t volts. And this expression is valid for all time values t greater than or equal to 0. Write it down, think over it. Let me know if you have any questions. Doesn't take the exact characteristics of a source. So the question being asked is, if the source is, let's say in this case, it's 100 volts, and the initial value would not be 100 volts. Yeah, that would certainly be the case. Depends on the circuit. Yeah, it could be like a Thevenin. You'd have to find a Thevenin equivalent network and then determine what the voltage or the current is for that component. Yep. Yes. Mm-hmm. This one. So the question being asked is, how does it reach 100 volts? Because that's the voltage that's being applied in series with that resistor. So initially, when it first starts out, and now we're not talking about time t greater than 0. We're talking about the time in the past, when the capacitor first began charging. So when the capacitor first began charging, there will be current flowing through the resistor, and there will be a voltage drop across that resistor. Okay, there will be a voltage drop across the resistor. The capacitor current or the capacitor voltage would not be 100 volts. It would start rising slowly. Okay, it'll start rising slowly. Eventually, it'll reach a point where it will reach 100 volts. It doesn't matter that the resistor is connected in series. Now, if the resistor was connected, if there are multiple resistors connected in the network, then yes, then some of the current would be flowing to the other resistors and there would be a voltage drop. Let's say there was a resistor in parallel. You have to look at the circuit without the capacitor connected. So if we look at the circuit, meaning we have to look at the Thevenin voltage from the terminals where the capacitor is connected. If you remove the capacitor, what is the voltage between those terminals? Analyzing Thevenin voltage between those open terminals. We did this problem earlier. Anyone? We just solved the entire problem based on this theory. It's 100 volts. Terminals are open. No current flows to the terminal, meaning there's no voltage drop across the resistor, meaning both ends of the resistors have the exact same voltage, 100 volts. So 100 volts is being applied to that capacitor. So even though when it's charging, the current would be small, the capacitor voltage would be small, but again, we are not looking at the charging analysis. Okay, if we were, it wouldn't be that difficult anyway. We just need to find tau, meaning R times C. The only thing we don't have is the initial starting point. Final value will always be 100 volts because we are looking at it from the perspective of the capacitor. We need to find the Thevenin voltage as seen by the capacitor. Okay, and that would be 100 volts. All right, any other questions? Okay, let's look at example 3. Example 3 is straightforward, but the setup is sometimes might cause, well, let's just talk about it, okay? So t less than 0, the only thing we are given is determine voltage for capacitor for time t greater than 0. Nothing else is given to us. And I'm going to go through this a little bit quickly because we only have 3 minutes left. So we look at the circuit, we see at time t equal to 0, the switch is flipped open. So time t less than 0, the switch was closed. If the switch was closed, all of the current from the current source is flowing through that short circuit. Nothing is flowing through the capacitor, right? Everything is flowing through that short circuit wire. Now, this is just a concept, okay? It's not real because we would never short out the terminals of a power supply. This is just to illustrate a point. The point is, if nothing is given, assume the initial capacitor voltage as 0 volts. Because we are not given any information about what that voltage is. It doesn't say it's a long time, doesn't state anything. So we simply state capacitor has not been connected to the source. We assume it's not connected for a long time. And therefore, VI or V0 is 0 volts. That's it. We're coming up on 12. If you have to leave, you can leave at 12. I'll just take a couple of extra minutes and write this out. And then switch flips open. When the switch flips open, we have a current source connected to the resistor. Capacitor C, current source of 10 milliamps. Final value of the voltage is given by 10 milliamps times the resistor R, which is 2000. And so VF, final voltage, is 20 volts. Tau is simply R times C. So it's 2000 times 10 microfarads. And so tau value is 20 milliseconds. And then we plug it into our expression for VC of t, Vf plus V0 minus Vf into e raised to minus t over tau. Plug in all the known values and reduce. Twenty minus 20 into e raised to minus t, 50t volts. This expression is valid for all time values t greater than or equal to 0. All right, I'll post the recording shortly after I reach my office. And then this is the end of chapter 4. See you all on Wednesday for chapter 5. Yes.
Yeah.
This would be a step response. That is correct. Yes.
How do you know that the current for the software right? You're using the 10 millions, right?
Yes.
But when the current split up, because is that the current across the capacitor?
So when it begins charging, yes, it will split up. That is correct. But eventually it will reach a point where it's fully charged, and that value would equal. Another way to look at it is that the resistor is in parallel with the capacitor. So the voltage across all three components will be exactly the same.
Oh,
right?
yeah.
At the end, the capacitor behaves like an open circuit,
Right.
meaning nothing is flowing through there. All of the current flows to the resistor, and that resistor voltage would be 20 volts, and that would be in parallel with the capacitor. Yep. Uh-huh.